Hello and welcome to NPTEL MOOC on fiber optic communication systems and techniques. In this module, we begin our study of optical fibers, which continues for a few more modules because we want to really understand how light is guided by the optical fiber and what kind of impairments does this fiber impose on the information that is traveling in the fiber. So, we need to understand to answer these questions, we need to first understand the geometry of the optical fiber, perhaps also look at different types of optical fibers. Not all optical fibers are used for communication, some optical fibers are used for sensors, some of them are used for biomedical imaging applications, some of them are used just for entertainment purposes. You take a bundle of optical fibers, then send light, maybe just cut them off and make a lamp kind of a thing. So, it is possible for optical fibers to be used for various applications, but since this is a communication course, our main goal will be towards looking at those fibers and their properties which are essential for communication purposes only. So, broadly we can classify these optical fibers as at least in the communication perspective, we normally classify them as single mode fibers and multimode fibers. Now, strictly speaking, this classification should be there for should be associated also with a specific wavelength range. For example, a same fiber which may be single moded or single mode fiber for a certain range of wavelengths can become multimode for a different set of wavelengths. So, however, in communication we do have specific wavelengths or wavelength bands over which we communicate. So, when we say it is a single mode fiber at 1550 nanometer, which is the most popular band of communication, wavelength band of communication, something that we are going to study deeply later on, then it is kind of understood that when we say single moded fiber, then it is used for, or it is assumed that for long distance communication it is being single moded in the wavelength band of around 1550 nanometer. Okay. Of course, you do get multimode fibers in that same wavelength or in a different wavelength region. So, what exactly is a single mode fiber and a multimode fiber? Are they same in terms of their construction? Actually no, their construction slightly differs, and it is in fact this construction which gives its a property of whether it is single moded or a multimoded. To understand that, we need to go back to our slab waveguide discussion that we had in the previous module, where we said that when you have a slab waveguide, there are different modes that are possible, and we actually talked about the even symmetric TE modes, and then there is odd symmetric TE modes, right. So, we talked about those modes, and then we said that when the mode number nu which we were using, when that nu is equal to 0, you get essentially a single TE mode, and then as that parameter kappa f times h, where h was the film thickness that we talked about in the last module, as this parameter kappa f, which is the transverse wave number times this film thickness, as it increased beyond a certain value, then the waveguide was now able to support not only the fundamental TE0 and TM0 modes, but it is also able to support the next higher order mode TE1 or TM1. So, we could of course make it single moded slab waveguide by restricting the product kappa f into h, or more prominently by playing around with the film thickness for a given wavelength, okay, because all these quantities are wavelength dependent. Kappa f depends on wavelength, everything depends on wavelength, of course h does not really, but there is a specific relationship between h and lambda that we looked at in the previous module, which tells us that if I want to restrict my waveguide for a single moded operation, then I need to ensure that h does not exceed a certain critical value. The same kind of idea goes even with optical fiber. So, once you fix lambda, then in order to make it single moded, you have to adjust the core core radius of the fiber. Okay. So, we will look at that, what happens when you change the core radius while keeping all the other parameters same, or when you have all the fibers manufactured, what happens when you change lambda. All these quantities are actually captured by what is called as a V number of the fiber. Okay. So, I am going to describe this V number now, and then we will derive all this V number and other parameters that I am going to talk about in this module in the coming modules. Okay. Here in this module we are going to look at the high level characteristics of or a bird's eye view of an optical fiber of optical fibers. But we need certain parameters, so I am basically going to write them down. Do not worry if you do not understand these parameters right away, the understanding comes in the later modules. Okay. So, anyway, so this V number, which is a very critical parameter in optical fibers, is defined as 2 pi by lambda, where lambda is measured in free space, that is, it is measured in not in the material medium which is made out of the optical fibers, but it is measured in the free space. So, you have 2 pi by lambda. Of course, you do remember that this 2 pi by lambda is the free space wave number of a plane wave that we were considering. So, that is represented by k 0 times a, where a is now the core radius, okay, times square root of n 1 square minus n 2 square, where n 1 is the maximum refractive index in the core, n 2 is the maximum refractive index in the cladding. Okay. So, we will talk about what is a core, what is a cladding shortly, but this parameter essentially governs whether my fiber is single moded or multi-moded. So, when this parameter is less than this value 2.405, okay, then the fiber will be a single moded fiber or single mode fiber. We shorten this as SMF, okay, and there is a standardized version of this SMF that is used a communication industry, that is called a standard single mode fiber, okay, that is specified by a certain standard. So, G656 is the standard that specifies the properties of the single mode fiber that is used for long distance communication purposes. Now, when this V number exceeds 2.405, okay, which can happen in what is called as multi-moded fibers or simply multi-mode fibers. Okay. So, this is shortened or abbreviated as MMF. M stands for multi, then M stands for mode, and F stands for a multi-mode fiber. Okay. Now, a fiber which has is a single mode fiber for a certain wavelength lambda, if I start reducing that lambda value, then clearly the value of V increases, because V is inversely proportional to lambda. Okay. So, there is a certain lowest possible value of lambda which we call as lambda c. If the wavelength lambda is greater than lambda c, then and for which V is less than 2.405, then over this wavelength region, then the fiber will be single moded or it will be a single mode fiber. However, when lambda becomes less than lambda c, okay, V automatically becomes greater than 2.404. Okay, this causes value of V to increase, and if V increases beyond 2.405, then this fiber becomes multi-mode fiber. So, it is possible for the same fiber to become single moded fiber over a certain wavelength region, okay, beyond what is called as lambda c, right. So, beyond lambda c for all those wavelengths, if the fiber is ensured that it is single moded at lambda c, then for every lambda that is greater than lambda c, the fiber will remain single moded. However, if you reduce the wavelength lambda, then the fiber will not be single moded, it becomes multi moded, because V is inversely proportional to lambda. And this magical value of lambda c, which is a design parameter that you can choose, okay. Of course, you can't fabricate it, you have to go to a optical fiber manufacturing plant to get these optical fibers with whatever magical lambda c that you want, but this lambda c in optical fiber communication systems or optical fiber systems is called as the cutoff wavelength. Okay. It means that for all lambda greater than lambda c, then the fiber will be single mode fiber, and when lambda is less than lambda c, then the fiber will become multi-mode fiber. Okay. Now, let us look at, we have already seen a picture of optical fiber, but for our purposes and understanding of how light propagates inside the fiber, this simplified picture might be sufficient. So, we have every fiber with having a normally a circular cross section. Okay. So, this circular cross section has an inner radius of a. This is actually a rod. Okay. So, except that these rods are not big ones that you can imagine, but they are very very thin wire like structures, as I have shown you in the introductory class. So, in case you have forgotten how an optical fiber looks, it is perhaps better to go to the intro video and then look at how the optical fiber actually looks in a practical version of it, right. So, you have a core you have a core of an optical fiber with a radius of a. Okay. I will tell you the typical parameters of this core radius shortly. Surrounding this core is what you have is called as a cladding. Okay. So, surrounding a core with a radius of b is what you have a cladding, and of course, surrounding the cladding you will have a coating, okay, which is an acrylic coating, that is just so that dust does not get accumulated on the cladding and then cause problems onto the light transmission property. So, it is essentially a shielding kind of a thing. So, you just put a small coating and you cover this entire coated fiber with what is called as jacket. So, if this is the single optical fiber that you are selling it to consumers or customers, then this is a typical fiber that you are going to sell them. Okay. Of course, as I have told you, no fiber is in a big telecom industry, no fiber is actually laid individually underground or overhead, okay, because that is just not economically feasible to do so. So, what we actually do is we form multiple fibers into what is called as a cable structure. Okay. There are various styles of cables that are used. So, this is just one style. We are going to look at optical cables later on, but each of those circles that I have drawn here are not really cores, they are actually what are called as loose tubes. Okay. So, inside this loose tube you have individual fibers. So, these are the individual fibers. Here these fibers just have a core and a cladding. Okay. They do not normally go with the coated, and these loose tubes are also differently colored for for visual inspection later on, but this is how an optical fiber cable looks like. As I have told you, this is not the only cable design, there are many designs that are possible, and this central member, okay, does not really carry anything. This is just for a mechanical support, okay, around which you have this particular cable with typically about 6 of them. Okay. I probably missed one circle, so I am going to put one circle out there. So, there are about 6 of them, not exactly, they are actually completely surrounding them, I have not shown it nicely, and each of these loose tubes themselves will have about 6 or 7 fibers. Okay. So, individual fibers. So, these are the thick cables that are actually laid down underground, and when you see those optical you see those in whenever there is an optical fiber installation, you will see those the big drums, right, and these big drums have this black cables. So, these are the cables that are actually wound on the big drum, and then the drum moves, some kind of a vehicle takes them along, and then the cable actually gets laid underground. Of course, the cable also has additional things to not just being holding the fibers, it also gives all the fibers a mechanical support, right. I mean, you might lay a fiber cable underground crossing one road to another road, but then you have a concrete road on top of it where the vehicles actually keep moving, then it if you just had the fibers below, then these fibers would not be able to take that mechanical stress, they would just break. So, instead of that one, if you encapsulate it with thick cables, these cables themselves are encapsulated in bigger cables. So, you do need to take kind of all those issues, because you want the fibers not to break, because you have to use these fibers for communication. Anyway, as far as mathematical analysis is concerned, if I were to do a complete mathematical analysis of this entire system, which involves a core, cladding, coating, jacket, including their material properties, including their thermal properties, mechanical properties, all those things, fluid mechanical properties, for example, if there is some fluid in between. So, the entire mathematical model will become too big to understand and perhaps not required for an initial course like this. Of course, there are specialists who sit and work on the entire mathematical models. The reason they work on these mathematical models is to understand the impact of coating thickness, say maybe the jacket, whether I can reduce the coating thickness because it is economically feasible to do so. Should I increase the coating because maybe I can decrease the decrease the cost of the fiber, but if the fiber keeps breaking, then my overall cost will actually increase. So, what is the optimum value of coating which can kind of compromise between what is the mechanical support that the fiber requires versus how durable that it can be. So, all these questions are answered by looking at in detail every property that is possible to study about these optical fiber cables, and most fiber manufacturing plants do have specialized people working on all this. However, the fundamental fact that is used in all these optical fibers is to guide light, and this guiding light is not by any arbitrary mechanism, but by this fundamental fact of total internal reflection. And to understand total internal reflection, it is perhaps just sufficient for us to look at a simplified optical fiber structure which consists of just a core and not even the cladding. Okay. We will assume that the cladding radius is so large compared to the core that we can kind of think of this cladding as being infinitely larger, or infinitely big medium. So, you essentially have a single rod or a circular rod structure which is the core with all of its properties that are of interest for fiber light guiding, and then surrounded by an infinite medium of cladding of different material properties. Okay. There are some sophisticated mathematical techniques which one has to use if the material properties are completely random, but luckily we do not have random material properties. At least those material properties which are of interest for fiber transmission are essentially the refractive index, okay. And we make certain assumptions in our analysis just to simplify it to get the crux of the idea. I want to understand how light propagates, maybe one or two features that are important for communications. I would like to understand it in as much simple manner as possible. Okay. Of course, a detailed model, if I want to know, then I can always go for a detailed model. Okay. So, the properties that are of interest for understanding light transmission is the refractive index. What kind of a refractive index does the core possess, does the cladding possess? Remember, these are the only two layers that we are going to consider now. Is this refractive index in the core can be less than the refractive index in the cladding? If it is less than the refractive index in the cladding, will light be propagating inside it? So, these are the questions that one would like to ask when one looks at light transmission inside the fibers. And as I told you, other material properties such as the structure of the fiber or the mechanical properties of the fiber are not important for the simplified cases that we are going to consider. They will be important. At least we will going to discuss one particular case where the fiber is taken and bent it. In that case, the mechanical properties, what is the mechanical property of the material that the optical fiber is made out of, how does it react to stress, how does it react to pressure, those things will become important later on. For now, we just need to know what is the refractive index, okay, and what is the core radius that may be at most required. Okay. So, what we are going to do is to construct or write a simplified structure of an optical fiber, and this circle is essentially the core that I am considering. Okay. So, this is the axis of the fiber, okay. And as you can see, I am going to make certain assumptions. I am going to assume that the entire core has a constant refractive index N1, whereas the cladding outside, right. So, this is the cladding that I have. This cladding has a refractive index N2 which is also constant, but it is less than N1. Okay. So, if I were to imagine myself being shrunk down to the level of a single micrometer or maybe nanometer scale person who is driving through this cladding and the core and plot their corresponding refractive index, what I will actually see is that if this is my axis, hold on a minute. So, if this is the axis that I have, then the refractive index in the cladding will be about N2, correct. So, this is N2 refractive index, but when it comes to the core, the refractive index jumps up slightly, okay, becomes the core refractive index of N1, and then when you go outside it becomes again N2. Okay. So, if I were to plot this in the normal axis way, so with r as the parameter, the radius of this one as a parameter, and taking r equal to 0, because this is symmetric. So, it is sufficient for me to take this as from r equal to 0. So, up to 0 to a, the refractive index is actually N1, because this is in the core region, and outside of this the refractive index is N2, which is of course less than N1. Okay. This type of a profile wherein the refractive index is essentially constant in the core as well as in the cladding and experiences a sharp step like change or step like discontinuity is called as step index fiber. Okay. So, again step index fiber can be single moded fibers or can be multi-moded fiber. Okay. It turns out that while the step index fiber is kind of simple to analyze, in fact it is simpler of the other type of profiles to analyze, this is not the only refractive index profiles that is possible, and it is in fact you will find out many different type of profiles. One of the profile that is very popular for eliminating intermodal dispersion in multimode fibers especially is what is called as a graded index fiber. In this graded index fiber, the refractive index of the cladding remains constant at N2, whereas at the center of the core the refractive index is N1, but N1 to N2 transition does not happen like a step, okay, but actually happens more like a graded profile. Okay. How is this bending? This bending curve is characterized by the profile parameter called alpha. This is the usual case for alpha equals 2, and for alpha equals infinity you will actually get back to the step index profile. You will also have additional types of graded index profiles that are possible by changing the values of alpha. So, alpha equals 1 will give you the linear profile, alpha equal to 2 will give you the parabolic profile, and different values of alpha, eventually alpha equal to infinity will give you the step index profile. Of course, this alpha is just a mathematical convenience that we are going to use. Real refractive index profiles do not look anything like this. So, if I were to look at a real refractive index profile, you will actually see something like this. Okay. So, there is a central dip because of the manufacturing process, okay, and so where it is supposed to be maximum, it is actually kind of minimum in the core itself. So, this is N2 and you can think of this as N1. Of course, this dip is unavoidable as I told you because of the manufacturing problem, and also notice that this is not as the refractive index is not going like a smooth curve, but rather has jagged edges. That is because the refractive index profile despite whatever the manufacturing improvements that we have made is not really giving you a smooth profile. Okay. Those surface roughness, if you were to examine them, would give you a jagged refractive index profile. Okay. However, to analyze these type of fibers with this kind of complicated refractive index profiles, you cannot really do it with analytical means. So, what you have to do is to put them onto some kind of a numerical solvers. Okay. And what I will do later on will be to tell you how to go about these numerical solutions, okay, but I will not be able to show you how to write codes, algorithms that will actually help you solve these type of real world problems. Okay. For our course, it is sufficient for us to consider things to be reasonably simple, but not too simple, so that we obscure the understanding of the fibers. Okay. Anyway, we come back to this. So, this is a graded index fiber. In communication, you will also find other type of fiber profiles, at least the ideal fiber profiles that are used. So, you have what is called as a trenched fiber, the number of trenches. So, this is a trench, the number of trenches may be more than one. So, you will have a multiple trenches. You will also have fibers which have this kind of a fiber profile. Okay. You will also have fibers with the refractive index profile which goes something like this with multiple trenches. Of course, this is symmetric, right. So, I have so far not indicated the symmetry here, but this is just how it would actually look like. Okay. So, these complicated refractive index profiles are used for dispersion management. Okay. Again, understanding of these with using mathematics is kind of difficult, or analytical solutions is kind of difficult. So, what you normally do is to put them through some numerical solvers. Okay. So, these are the different refractive index profiles of optical fibers that you normally encounter, and what I am going to do, as I was telling you, is that I am going to look at a basic bird's eye view of how light is guided by the fiber. Okay. And in order to do that, it is sufficient for me to just consider. So, this is the fiber, this is the core. I am going to also write down the cladding here. See, please note that this distance is not realistic. Okay. The core is usually quite smaller, the cladding is usually quite larger in circle, but just for our understanding, if I were to just imagine that this is my optical fiber, because I want to introduce a quantity called acceptance angle. Okay. So, this is just the optical fiber with this axis. I have exaggerated the core medium over here. What I have is that an incident light usually comes from outside the fiber, right. So, I wanted to indicate that one, hence I have indicated this optical fiber like this. Okay. This incident ray of light strikes the core cladding interface, the face of the optical fiber at an angle of theta 0. Outside medium, let us call the refractive index as n0, inside the core has a refractive index of n1 and the cladding has a refractive index of n2. Now, what happens when this ray of light is incident at this angle theta 0? Clearly, Snell's law will tell me that there will be a reflection into this one, or sorry, refraction into the medium. So, there will be some amount which is refracted. Of course, there will be some amount which is reflected, but we do not really worry about that reflected part. So, what we are concerned is the amount of light or the ray of light that is refracted into the cladding now. So, the cladding, now this axis is the normal to the interface, right. So, the cladding is actually making an angle of, let us say I will call this as phi, okay. Maybe if you want I can put this as phi 1, and with respect to core and cladding, now this is the core and cladding, correct. This ray of light which is travelling inside the core has made an angle of theta 1. And now what I want to understand is that if I were to have this ray of light, the second ray of light which is travelling inside the core hit the core cladding interface at an angle theta 1, what happens if this angle theta 1 is greater than the critical angle of the interface between core and cladding? If it is greater than the critical angle, we know that this ray of light actually goes back, okay, because it is totally internally reflected and now arrives at the lower interface of core and cladding. There is nothing special about this one, because if this has refracted by this angle theta 1 because of total internal reflection, this angle would also be theta 1, and we have already established that this angle theta 1 is greater than the critical angle for the interface between core and cladding. Therefore, the ray of light further gets totally internally reflected, and then after passing through this zigzag path, light is guided from one point, that is at the input of the fiber to the output of the fiber. Is it possible that there is any limitation on this angle theta 0? That is, if I were to consider this angle theta 0, light at this angle theta 0, will this light be propagating inside the fiber? Or if I consider light at this angle, we know which is very short angle theta 0, will light be propagated? These are the questions that we will like to answer in the next module, okay, when we discuss slightly more about this ray picture of light propagation inside the fiber. So, until then, thank you very much.